Alright, welcome to this video in which we're going to review the data type of a heap, a min heap or a max heap. Specifically, we're going to focus on binary heaps. And we're going to look at that as an implementation of an abstract data type called a priority queue. Now, a priority queue is very similar to a standard queue. Standard queue we know to be a first in, first out data type. And in a standard queue, all entries in the queue are treated equally. But in a priority queue, we have entries added in with different priorities, and we want to handle the elements in the queue with highest or lowest priority first. And so a priority queue is a type of queue, and so it's going to have very similar operations to a normal queue. In Java, we call these offer and poll, or in other cases, we might call them enqueue to add to a queue and dequeue to remove from the queue. And we're also going to consider a secondary operation that we might be interested in performing is once an entry has been added to a queue, we might want to adjust the priority of that entry by decreasing or potentially increasing it as well. And we call this operation the decrease key operation, to decrease the value of that key. So if we want to implement a priority queue, and maybe all we have at hand are some list structures that we're familiar with, there are two possible ways that we could think of implementing a priority queue. One way to do it is to use an unordered list. In this case, we're just going to put all the elements into the list in no order at all. That means adding a new element to the list is actually not that hard. We just throw it on the end of the list since there's no order maintained. So as we say here, that's going to take us a constant time, or big O of 1. But finding and removing the minimum element is going to be trickier since we have to search the whole list now and then maybe shuffle things around afterwards. So this is going to take us order n, or a linear amount of time in the worst case, to find and remove the minimum element. So one of our operations is not that expensive, the other one is. And then if we want to maybe save ourselves some effort, we might say, well, let's go ahead and use an ordered list, keep the elements in order. The idea there is that in so doing, removing the minimum element might be as simple as deleting the last element on the list, or another way of thinking of that is deleting the top element of a stack. That's pretty easy. The problem then is when we add a new element in, we need to add it into the appropriate location, which itself might involve iterating over the list and possibly shuffling nodes around, or elements around. So again, in the worst case, this operation will end up being an order n operation, the add operation. So what that means is we have these two different ideas of implementing our priority queue as a list, and both of them come with a cost, a drawback, that drawback being that one of their operations is expensive at the cost of the other. Sometimes we might think, well, that's not that bad as long as we have some way to know which operations get performed more often. In some data structures, this might be something we could rely on. Unfortunately, in a queue, typically the idea of a queue is to fill it up, but then also to empty it. So a queue, most of the time, are things waiting to be processed, things waiting for their turn. And so usually you perform an equal number of adds as you do removes over the lifetime of the queue, meaning we're not going to favor one or the other of these implementations. We're not going to have an instance where we're going to do a whole bunch more adds than we're going to do deletes. And again, that is something that might be true of a lot of other data structures, where data structures that are used to represent databases, for instance, which is very common, the databases often grow in size and rarely shrink, and so you might then say favor idea 1 here. Okay, where adding new elements is cheap, but removing elements is expensive. However, the purpose of going through these two possible implementations is to focus on the maybe third option, is don't use a list at all. So if we don't want to use a list at all, how can we do that? Well, maybe we can use a tree. And the type of tree that we're going to use has a special name, which is a heap. And so we're going to look at a heap. And there's actually two different kinds of heap depending on whether you want to keep the minimum element on top or the maximum element on top. And we call these a min heap or a max heap. But I'm going to focus on min heaps in this video. The one that I actually have listed here is also a min heap if we use the normal standard ordering of our symbols in the alphabet, A being the least valued, Z being the highest value. So this heap here, as I've got defined here, a binary heap can be defined by an invariant, as we've defined other data structures in this series. Remember, an invariant is a property or a set of properties that does not change or does not vary as operations are performed on our data structure. So here we have a heap data structure. What properties make it a heap are the properties that will stay the same as we add elements, remove elements, or perform other operations on our heap. And the two properties that are the invariant, the two properties that will remain the same over the lifetime of the heap are these two properties here. And altogether we'll call them the heap invariant, but we usually split them into two properties, the heap property and then the complete left-loaded binary tree property. The second one we might be pretty familiar with already, but the first one, the heap property, is the one that actually characterizes the heap. So in this one it says here that the value of the item stored at the parent node is always less than the value of the item stored in the children nodes. And so again, I say here, this is what defines a min heap. If we change the less than to greater than, then we have a definition of a max heap. Again, one keeps the minimum element on top, the other one will maintain the maximum element on top. We can verify here that this heap is indeed satisfying the heap property. A is less than B and C, B is less than D and E, and we can verify for all of the nodes here that the values of the children are greater than the values of the parent node. Now, the complete left-loaded binary tree property, that's got a lot going on there, but we've taken a look at a few of these definitions in an earlier video. Binary tree, yes, this tree is a binary tree. Each node has no more than 2 children. That makes it a binary tree. It's a complete tree, at least satisfying one of our definitions of complete, in that all the nodes have exactly 2 children, except for nodes in the last 2 levels. On the last level, there are no children, and in the second to last level, there are 0 or 1 or 2 children. We permit any number there. The one property we don't have is that the last level is not left loaded. And to be left loaded, what that means is all of the nodes on the last level should be loaded from left to right. And we can see here our I and our J are not in the appropriate location. If we then move them over here, we now have a complete left loaded binary tree. So this here is truly a min heap. What we had before satisfied the heap property, but not the complete left-loaded binary tree property. And so this is a heap that satisfies both properties of the heap invariant. All right, so given that we've defined the invariant now, we can start looking at how we might add or remove elements from an existing heap. And so here I have an existing heap, and again, this one we could, if we like, verify that the value in every parent node is less than the value of its children nodes. Again, take a moment to just quickly verify that. You'll notice that even though that is true, there is not any strict ordering amongst the other elements. For instance, the left children is not always less than the right. It's true here, but it's not true down here. We'll also notice that though high-valued nodes tend to be at the bottom, sink to the bottom, and low-valued nodes rise to the top, that's again not always a guaranteed rule. Here we have a 6 that's lower down in the heap than this 9 and so on. This 10, 12, and 9 are all higher up than this 7, for instance. So the heap property does maintain some order amongst the elements, but it does not maintain a very strict order among the elements. It doesn't keep them all in order to enable us to retrieve the minimum element. It only keeps them in the sort of partial order as we go. Okay, so that's just, again, taking a look at a heap, the structure of what a heap looks like. But now the idea is, say we want to add to this heap. And we don't want to violate the heap invariant, the two properties, the heap property and the complete left-loaded binary tree property. We don't want to violate them if we can help it. And so usually what that's going to mean in a heap is we're going to say, hey, if I want to add to this tree, if I want to add to the heap here, and I want to keep it a complete left-loaded binary tree, then the only way that I'm going to be able to do that is to add an element into this one location here. I have it indicated with the question mark. If I add anywhere else, I'm going to violate the complete left-loaded binary tree property. So basically what that means is no matter what we do, when we add an element, we're going to add it here. What that means is, depending on which value we add here, there's the potential that we could violate the heap property. So here I'm adding it as a child of the node 10. If I added, say, a node with value 20, 20 is greater than 10, I'm okay, I'm in the clear. So some of the time this will be a safe add and we're good to go. Well, here's an example maybe with the number 14. Okay, so this is a safe add and we're done when we do this. However, it's possible that the number that we add is now violates the heap property by being less than the parent. And to do this, we're going to now perform an operation that's known as the bubble up operation. I've got it stated here in some simple pseudocode. While the current node is less than the parent node, we'll just swap the current and the parent node. So we have here our 1 is less than our 10, so we swap them. In this case, the current node is now moved up, and we'll do it again. If the current node is less than the parent node, we'll swap them. Okay, again, the current node is now moved up, so we'll do it one more time. If the current node is less than the parent node, we'll swap them. Well, in this case, it's not less than the parent node, and that's how we know that the node has now settled into place. If it ever reaches a place where the parent node is less than it, then we're now in a good spot, and usually the bubble up operation terminates here. The key to a heap, or one of the reasons we use a heap, is the operations that we perform on it are going to be more efficient than the order n operation that we saw in our earlier examples. So to do that, we're going to need to perform a little bit of analysis on the operation itself. So let's think a little bit about how this operation might be carried out. Now, it's very common in when working with trees for these operations to be carried out recursively. And the reason for that is the recursive stack is going to allow, the recursive call stack that is going to keep track of where we've been in our tree as we traverse or move about the tree. Now, if we don't want to use recursion to do this, then typically that means we're going to need to use a stack of our own to keep track of where we've been. Now, when we're implementing a heap, there are some clever implementations that may not need to rely on all of these techniques. But for the moment, let's think of the heap as a linked structure. And so we might start at the root node, and when we do our add, we're going to have to recurse down the tree to the location where we want to add. Then we're going to make the add there, and we're going to recurse back up. So we can think of the add as consisting of these two trips. First, the trip down to the location of the add, and then the bubble up operation is carried out as we traverse back up, possibly swapping as we go. Now, an important thing to note here is the position that we're adding to will always be on the deepest level of the heap. So if our heap is of depth D, then we might say here that the depth of the node we are adding is also at depth D. We can also see here that the cost of moving down one node at a time to that depth is also D. We will visit D nodes along the way on our way down there. As the recursion unwinds, we will also visit those same D nodes on the way back up. For each node, it's potential that we will visit it twice in this trip. In addition, as we visit each node, we're only going to perform a constant amount of work. Now, on the way down, we're mostly traversing, but on the way back up, we might be doing some swaps. Well, remember that a swap operation itself is only a constant amount of effort. So what this means is the worst case cost of the add operation is going to be big O of D, where D is the depth of the node added, or D is the depth of the heap, since the node is always added to the lowest level. Well, let's recall from an earlier video that the depth of a complete binary tree with n nodes, we went and calculated this, is equal to D, which is the floor of log base 2n. Now, this, of course, is logarithmic in the number of nodes, meaning that the cost to add an element to a heap with n elements in it is big O of log n, which is a good improvement on order n if that was the cost that we had prior. All right, now let's take a look at removing from the heap. Moving from the heap, we're going to rely on some of the same ideas that we applied in adding to the heap. First of all, when we want to remove a node, we're again going to use the same principle, but by saying let's try and not violate the complete left-loaded binary tree property. And if we don't want to violate that, that means there's only going to be a single node in the tree that we're going to be able to remove. And that's the one I've got here highlighted in green. Unfortunately, the big problem is when we want to remove from a heap, recall that we only ever want to remove the one with the highest, or in the case of a minimum heap, the lowest priority. So the node we actually want to remove is the root node, the 0, and it's always the root node that we want to remove. Keep in mind that removing the root node is probably the worst node that we could remove. If you want to kill a tree, a good way to do it is to delete its roots or dig out its roots. And so that's probably a good thing to do here. If we delete its roots, it's probably going to destroy our tree, and certainly that seems to be the case. So actually, when we want to remove from the heap, we want to avoid deleting that root, even though that's the node we want to remove. So instead, the first thing we're going to do is we're going to perform a swap on the root with the node that we're safely allowed to remove, which was the 10. So that means the 10's moved up, and then we can delete the 0 after it's been put into that location. Now, of course, this swap, even though it doesn't violate our complete left-loaded binary tree property, it does very likely violate our heap property. And so now we're going to perform an operation known as the sync down operation. And again, I have the sync down operation stated here using some pseudocode. This one says, while the current node is greater than a child node, there's a little subtlety there. There's two children here, so which one? Well, either one. If it's greater than either one, then what? Swap the current node with, and now here specifically I'm stating the least child. So we can see here the 10, it is greater than both of its children nodes, the 3 and the 1. But if we were to swap the 10 with the 3 would still be in violation with the 1. It's greater than 1. So the only way we can ensure that no violation is created by promoting one of our children is to promote the least child. And so we will promote the least child here, 1. and sink down the 10. Well, again, while this is still the case, now 10 is greater than 9, but not greater than 12. Again, we swap with the least one until the 10 settles into place, where now that it's at the bottom, has settled into its appropriate place. When we want to take a look at how many operations it's going to take to remove an element from a heap, again, we want to think of it as consisting of possibly 2 trips. First, we need to swap down. How we swap down, if we carry this out recursively, that might indeed mean traversing down to the appropriate location. However, if we can do that maybe easier, then we still have to perform the sink down operation after we carry out the swap. And that one, again, will potentially sink all the way to the bottom level, where the bottom level is going to be depth D. So again, along these trips, we're going to visit these nodes potentially twice along the way. And again, we're only doing a constant amount of effort at each visit. So the worst case runtime of our remove then is going to be order of D, or order of the number of nodes that we visit in our traversal. Again, using the same principle as before, the depth is going to be logarithmic, so the cost of doing our remove operation is also going to be logarithmic. Altogether, this means that we have now an add operation that is logarithmic and a remove operation that is logarithmic, and both of those are better than linear time. Neither of those is better than constant time, but we might be willing to sacrifice constant time on one of our operations if it improves the linear time operation down to logarithmic. And indeed, that's the case for a lot of cases where we might want to employ a priority queue. And so a minimum heap is the standard implementation of a priority queue. All right, the final operation that I want to look at with relationship to a heap that's really of importance, and is really not one of the straightforward operations to implement, is the decrease key operation. Now this operation becomes relevant when, after adding an element to a heap, you want to decrease its value, decrease the priority. Usually this means moving it closer to the front of the priority queue. And if you're faced with this problem, you might realize that this is at first is actually not a very straightforward or easy problem to solve. So you can maybe think about it yourself, but the thing that causes it to be a little bit tricky is finding the node that you want to decrease its value of in the heap. Okay. And one reason why this is a little bit tricky is the heap doesn't give us a good way to search for elements. Unlike a binary search tree, which we'll look at in a future video, which is designed for searching for elements in an efficient way, a heap is not designed to look for elements. It is designed for removing the min element in an efficient way. So if you don't have your structure designed to be searched in an efficient way, then that means you're probably left with a simple sequential search. With a tree, that means, let's say, doing one of our traversals. So maybe we will do a pre-order traversal where we will check each node as we encounter it to see if it's the node that we're looking for. Of course, the cost of that search is costly, which is possibly order n, and we maybe don't want to spend that much time operating looking for that node just to decrease its key. Now, some other operations we might encounter might say, well, maybe we want to delete that node instead of decreasing its key, and then we could just add a new node in with the new value. Well, again, if this deleting idea would require us to know the node, where the node is, and again, we'd have to perform this costly search operation to find the node. So both of these options are not really available to us. Searching for the node is too expensive, and so without coming up with a better way to do this, we might have to say, no, we can't permit decreasing key operation, it's too expensive. However, we get a little bit of help if we are able to rely on another data structure. And the data structure that we're going to rely on is, again, one we'll look at in this series of videos. It's a map, but more importantly, a map implemented as a hash table. When we have a map implemented as a hash table, if we know which key we want to decrease, we can look it up in the hash table, and that will give us a reference directly to the node of the heap that we might need to modify. So the idea here is the first step of our decrease key is we're going to use a map to find the node in the heap that we want to modify. Once we've found the node, then we can do the operation decrease its value or increase it. Sometimes we might want to increase it. And when we do that, that's going to potentially violate our heap property again. So to correct that, we're going to once again rely on a bubble up or sync down operation to correct that invariant if it is violated. So once again, the cost of the decrease key operation is now dominated by the cost of this bubble up or sync down, and this is primarily because we've used the map to save ourselves the cost of this order and search. Otherwise, the whole operation would be dominated by this order and search, and it would take order and operations. However, since we've saved ourselves that search with using a map, we can instead perform the decrease key operation in logarithmic time. And this is actually going to be very useful in the performance of a number of algorithms. Most notably, Prim's algorithm to find the minimum spanning tree of a graph, and Dijkstra's algorithm for finding the shortest path between 2 points in a graph, both of which use a very similar loop structure, and a minimum heap or a priority queue becomes a very useful data structure in both those algorithms, both of which we will take a look at later on once we start talking about graphs. Okay, let's just do a quick example of the decrease key operation. Let's say here we want to decrease the value of 16 to 2. So we begin by going ahead and just finding it with our map and decreasing it. Finding with the map was as simple as us finding it with our eyes. You find it very quickly, easy access. So we found it. We didn't have to traverse to get there. And then we changed its value. Now that's all that's left to do is to fix the invariant that we have violated here by bubbling up this new value 2. So we will swap it with its parent so long as it is less than its parent. Swap it again, but we see now that it settles into this location here. It's not the minimum element. 1 is the minimum element, but 2 has settled here as a child of that minimum element. All right, I want to finish this video by talking a little bit about how one might implement a minimum heap. So once you've decided that a minimum heap is what you need for your purpose, your priority queue, you might say, how am I going to go about implementing this? With a lot of trees, the instinct is to maybe implement it as a linked structure. At least that's my instinct. But that is not usually the advised route to go for a heap. And in fact, for any structure, we usually have available to us an array implementation or a linked structure implementation. And for a heap, heaps lend themselves very well, more than any other tree, to an array implementation. And I'll show you why that is right here. First of all, keep in mind that our heap is, again, a left-loaded binary tree, complete binary tree. And importantly, and this might come up in a future video where I want to do an exercise related to heaps. But we can do a quick little example here. If we look at a heap, we can sort of look at the order in which elements would be added and the positions that they would be added to. So our first element we know is added as the root of our heap. And next here in the left position and then to the right. So again, 4, 5, 6, 7. And since we add them in this very predictable order, this is sort of like adding elements to a list. Adding them in the order we would add elements to a list. And in fact, that's the idea. Say we had a list instead, we would add it first here, then here, and so on. And so our idea with implementing a tree as an array is if we have an element that's in position 6 of our tree, we just put it in position 6 of our array. Now luckily, our heap fills our elements up in this order, fills the tree up in this order. What that means is we don't ever leave any empty spots in our array as we fill them up. If we filled up to position 11, we know the next element we need is in position 12, and then the next 13, and so on. Likewise, if we want to delete, same thing. The only one we can delete is this last one, the one on the end. So because of this idea, it becomes quite convenient for us to implement an array, our heap as an array. And so here again, I have just this example with this heap here, and I've sort of color-coded it for us to see how that organization goes. 1 is the first element of our array, then we have 2 and 3, which are our 3 and our 9. And we can see here that we can quite easily find the element that we're looking for in our tree if we knew where it belonged before. We can find it in our array. A few points to note. We know in this complete binary tree the number of nodes on each level is a power of 2. And so the blocks that we have here are also powers of 2. 1, 2, 4. The purple block would be 8, and the next block would be 16, and so on. The one thing we lose in this array implementation is easy access to our children and our parents. In the linked structure, we actually have links, references from a child to a parent. But in the array, we only have virtual links, potential links. And that means we have to do a little bit of math to calculate where a particular node is. Let's see if we can verify this math for us by saying, okay, say I'm in position 6. Where are my children? Well, looking at our indicator right here, my children are in position 12 and 13. And what we might notice is one of those is going to be 2i, and the other one is going to be in 2i plus 1. Okay, 6 to 12, 2i plus 1. Then these are our children. This might be my left, and this might be my right. Okay, and then we might also ask, well, where are my parents then? Where are the parents going to be at? Well, my parent, if I'm in position 12, it looks like my position is going to be in index I over 2. And if I'm in position 13, it's also going to be I over 2, as long as we treat this as the floor. Okay, the floor. Or integer division is another way of thinking of that. This is my parent. Now, notice that I've done this, I've gone and calculated this math here. Some of you might say, hey, wait a second, that's not what it said on the slides at all. What are you doing here? You're making stuff up for me. Well, maybe I am. Maybe I got it wrong. Well, actually, the reason why my math over here is going to work this way is because I start at 1. And I could have started counting a different place, and in fact, when we deal with our arrays, we usually start at 0. So if we started at 0, which is probably the way that we wanted to implement it in the first place, we might get some different numbers here. So let's try it again. What happens if we were in position 6, but let's do it again. So let's say 0, 1, 2, okay, 3, 4, 5. Okay, this is our 6. Now we should be careful here because these aren't actually 14 and 15, right? They are actually 13 and 14. So before we had 12 and 13, now we have 13 and 14. So if before it was 2i, now it's 2i plus 1 and 2i plus 2. And then same thing with our parent here. If it was I before, now we have to go I minus 1. Okay, so our 13 becomes a 12. Our 14 becomes a 13. And then we divide by 2. Okay, so these are more likely the values you'd want to use, because if you were implementing this, you would implement it with a zero-based indices on your array. Okay, so again, this is usually the standard implementation of a heap is as an array. It's much simpler than implementing it as a linked structure. However, as a future exercise, I'm going to think about, say you were a linked structure, say you did implement this in a linked structure, and say you wanted to go to one of these positions. So say you wanted to go to position 10 here. You'll notice in the linked structure, to get to position 10, you would have to go left, right, left to get there. And so maybe I'll leave this as an idea for you to think about here. We have here, if the value I want to go to, this was starting with 1 indexing. Okay, I know I've changed my tree here. But if this is position 1, and we wanted to get to position 10, we needed to go to 1, left, right, left. So it says here that the path, if our n, or let's do it this way, if our n is equal to 10, our path to get there was left, right, left. And the question that I'm going to pose for you, and maybe take this away and try and think of this on your own, is I want to know what the path is to get to position 42. Again, labeling this tree starting at 1, 2, 3, 4, and so on. What is the sequence of lefts and rights I need to go to get to position 42? Now I want you to go and figure that out. See if you can figure it out. Okay. Now if you can, one way to do it is just draw this tree until you get to 42 and figure it out. Now that's going to take a little time, but you can get there. But that's sort of cheating because afterwards I'm going to ask you what's the value, or what are the sequence of left and rights for this. 1, 3, 3, 7, and of course that's going to be a longer one, and you probably don't want to write out a tree with 1,000 entries in it. Okay, so you don't want to do that, so you want to figure out a technique, a rule to figure out what are the sequence of left and rights to get to the position I want to belong in. And I'll give you the secret to that in a future video. All right. I am going to practice our heap operations, our add and our remove, in another video. But before I do that, I am going to want to take a quick aside to talk about random number generation and generate some random numbers that I'm going to be able to use in the rest of this video series. All right, thanks for watching this video, and we'll see you in the next video.